All right, good morning. Welcome back to another lecture. Um, there's a warm-up question for you to think about as we're getting started. We'll talk about it first. Just want to start with mentioning the first quiz is this weekend. So the way the quizzes work, tomorrow at I think noon, Winnipeg time, the quiz releases. And you have from Friday noon until Monday midnight to take it. Any 15-minute window of your choice in that time period, Friday noon until Monday at midnight, you can start the test. You get one, or start the quiz. Sorry, start the quiz. One attempt at the quiz, 15 minutes. Open book. Yeah, so make sure you take some time between Friday and Monday to get that done. It covers all of the material we've done so far. I have a question in chat that I don't completely understand. What's the syllabus for the same? The coverage for the quiz is everything we've done so far, the first 4 lectures, including today. And there are office hours today after class if you want to ask about anything. Also on Monday, if you want to ask about anything. So if you're worried about the quiz, if you're working on things and you still have questions, you want to ask either today or Monday, I will be around for the optional drop-in office hours. Okay, let's start with this warm-up question. So we have an open statement. N is divisible by 2, right? Not a proposition, because it's not true or false until we know what the value of n is. And we're trying to claim for all non-negative integers, q of 4 times that integer is divisible by 2. So let's take a look at that. Our main tool here is going to be the rule of universal generalization. That was what we talked about at the end of class last time. If we can prove something for an arbitrary member of a universe, then it holds for every member of the universe. So we want to pick C in the non-negative integers arbitrarily. And if we look at 4 times C and divide it by 2, that's going to come out to be 2 times C is a whole number. Therefore, since 4c divided by 2 is 2c, 2c is a whole number, that means 4c was divisible by 2. And now, by the rule of universal generalization, for all, because I picked an arbitrary C in my universe, for any n in the same universe, the same exact proof would work. You can pick any one you want and plug it in here. This exact procedure will always work. Q of 4n. Okay. How do we feel about that one? Questions, concerns? Okay, so I want to make a bit of a distinction, just so it's clear. This style of proof, where there's sort of a flow, there's a story going on here. I'm picking a C, I'm doing this, which I'm saying is a whole number, therefore this, and then I'm using the rule of generalization, rule of universal generalization, I get my conclusion. This is one style of proof. This is the story that I'm telling. I'm explaining to you why this is true. The other style of proof we're going to see in this course, and we will do both, so I want to make sure to give you examples of both, is a more formal line-by-line argument, where we justify each line. So let me do another problem now. This also lets me introduce our second important rule. And this is going to be a formal proof of this statement. So here is the statement. For all x, p of x, and q of x, logically implies for all x, p of x, and for all x, q of x. Okay, so these are two different statements, right? Here the and is inside the parentheses with the for all out in front. Here there are two different for alls, but this statement says if you have the first, you're allowed to conclude the second. And I'm going to prove this logical implication using our rules of universal quantifiers and our implication, our laws of logic and our laws of the other one. I'm blanking on inference, laws of inference. Okay, so we're going to start with our premise, right? If you have an argument, all of the things you are assuming are your premise. So 1 for all x, p of x, and q of x. That's a premise. Okay. Now, I have a for all statement. My second rule of universal quantifiers is anytime I have a for all statement, I can pick a particular value, and it'll be true for that value. So since this is true for all x, I can pick a particular value, let's say c, and I can say p of c and q of c is true. And this is true by the rule of universal, not generalization, but specification. I've specified this was true for all x, which means it's true for c. C is just a particular x that I've chosen. And since it was true for all of them, it's also true for c. Do we mention what is c? We don't have to here. C is just a particular value that we've chosen. All we need to write is what I'm writing now. We are recording the class, yes. I'm not recording it through WebEx. I'm recording it separately, and that's because I don't like how WebEx records everything. My picture ends up small, so I'm sorry that the little recording warning is not active, but we are recording it. Okay, so now, remember my goal is to prove these two things for all x p of x and for all x q of x, and then conjoin them together. So my next step is going to be to isolate. I have this and statement, but I want to look at just one of these things at a time. So I'm going to look at just p of c. I have p of c and q of c. I just want p of c. And this is going to be by the rule of conjunctive simplification. Conjunctive simplification. This is one of our laws of inference that I'm using here. And now I have p of c, but c is just an arbitrary member of my universe. So now I can use my law of universal generalization universal generalization to say not just P of C, but for all x P of x. Okay, so now I have half of what I want up here. I've gotten for all x P of x, that's good. Now I want to do the same thing to get for all x Q of x. So that's going to be 2 steps again. First, from line 2, I can again use the rule of conjunctive simplification. And I can even indicate from line 2, just so that it's clear, I'm not using conjunctive simplification from the previous line, because there is no conjunction here. I can't use it on this line. I'm using it from line 2, which is why labeling your lines is good. And then line 6, I can do the same thing for all x Q of x. This is again my rule of universal generalization. And then I need one more line. Line 7. Now I have for all x P of x. I also have for all x Q of x. I want to combine them somehow. I can combine them using the rule of conjunction. This is by the rule of conjunction. Okay, so here is my formal, and maybe I'll add by lines 4 and 6. Here is my formal proof of this logical implication. Each step has a justification of where it came from using one of my rules. And both of these count as proofs. This is the type of proof we'll focus on earlier in the course, a very rigorous formal proof step by step. This is the type of proof we're going to shift to as we move on through the course, more of a conversational proof, describing what's happening, much more natural, a little bit less formal. But remember, the goal of this course is to talk about how we prove things, what the expectations are, and that always requires multiple people in the conversation. You need a proof writer and a proofreader. Sometimes that's the same person, that's fine, but there's always 2 sides, and there's always communication. Okay, so basically we break them apart using laws and then bring them together to satisfy the other side of the statement. Yes! Okay, I'm going to expand on this question a little bit. What's going on here? What's going on here in the larger sense? So there's this problem with teaching this stuff, which is when I write up this example, it looks nice and pretty. I write the statement, I write all the steps in order, and it comes out and it's the answer. But how did I know how to do this? How did I get each step? Why did I know it was this, then this, then this, then this? And the answer is because I did it ahead of time. It's in my notebook. Here's the notes I use when I teach from, and I prepared it ahead of time. I figured out what I wanted to write. And now that I'm showing you, it looks like, oh, I knew it the whole time. But the process of writing the proof is step 2. Step 1 is figuring out the proof. And when you're figuring out the proof, there's a lot of noodling around. There's a lot of just trying stuff, even if it doesn't work. So maybe when I started out this problem, I might go down some wrong paths. I might pick different rules that might just not end up helping. You could use things like, if instead of the rule of conjunction, I had used the rule of disjunctive amplification, then I would have gotten an or here instead of an and that wouldn't have been helpful. It would have been a path I went down that just didn't end up working, and that's okay. Step one is to just try a bunch of stuff until you see how the proof is going to work. And as you do more and more proofs, you get more of an intuition for what might be helpful and what might not be helpful. And then it's really important that these are separate steps. After you do all of your exploration, step 2 is to actually sit down and write the proof and make it look all nice. That's the secret to writing proofs. You want your proofs to make you look like you're a genius, right? Ah, yes, teacher is so smart. Teacher knew how to do this. 7 steps, but he saw them all right from the beginning. And look how brilliant he is. But it's not true. It's all hiding the lie that we started by just messing around, just trying some stuff, seeing what can happen, got lucky, struck the right argument, put it all together, and then wrote it up nice. Can you do it the other way around? Can you write the right side as the left side? Do you mean this argument, or do you mean switching where I put my symbols and where I put my words? Verification for that. Proving it from the right. Okay, so this is a statement, right? I'm claiming that this implies this thing. This is a separate statement for all x p of x and for all x q of x. Oops. Q of x logically implies for all x p of x and q of x. Okay. We can try and prove the statement too. In fact, let's do it because that's a good example. Second question from chat. In tests, do we need to show your attempts to figuring out the proof, or just do that on scrap paper and show only the proof? I'm not sure is the answer to that. You will never be penalized. You shouldn't be penalized for showing your work. So if you're trying out some stuff and it doesn't work, and you include that, and then you show your final answer, that's fine with us for the test. I don't know exactly how we're going to word test questions, so I don't have a good answer for that for you yet. Okay, so separate statement. Chance that I screw something up here because this one's not in my notes. I haven't carefully done it. So we're going to go on intuition. We're going to talk about what we're hoping to prove and how it could work. So, okay. Where are we going to start? We only have one premise. We should start with our premise. And this is by premise. And now I'm thinking, right now this ampersand is in my way because I want to use something like the rule of universal specification. But I can't because this ampersand is in the way. Good question in chat. Let me get to that after this one. So since I have an and, I can pick either side. So let's pick one of them. This is true by my rule of conjunctive simplification. And now if this is true for all x, then I can pick a particular x. This is my rule of universal specification. Can you use laws as well? Yep, laws of logic are fine, laws of inference are fine. All of that can go in. Okay, so I have P of C. I'm going to stop there for now. I'm going to go back to this for all x q of x. this was a rule of conjunctive simplification coming from line 1. And now, again, for all x q of x, I'm going to pick a particular x. I'm going to pick c. And importantly, it's allowed to be the same c. Right? This is true for all x. This is true for all x. So I'm allowed to pick the same c for both of them. That's fine. Rule of universal specification. And now I have P of C and Q of C. So I can combine them. What did we decide that rule was called? Oh, it's right up at the top, rule of conjunction. That's using lines 3 and 5. And now, last but not least, I can use my rule of universal generalization to say that this is true for all x. Okay. So this one I ended up getting pretty quickly. That's, again, due to my experience. I've been doing these proofs for a long time. I was able to see ahead of time some steps that might be useful, and they just ended up working out for me. I did not know when I wrote down step 1 what every step was going to look like. I didn't know how many steps there were going to be. But I just sort of followed what my intuition said, and it ended up working out well for me. So there's this really good question in chat. Just because one statement logically implies the other does not mean it works the other way around. That is completely correct. In this case, we have proven both directions, which means we have proven the statement for all x, p of x, and q of x is logically equivalent to for all x, p of x, and for all x, q of x. We've only proven that it's equivalent, logically equivalent, because we've proven both directions. But the two directions are independent. One could be true, the other could be true, both could be true, neither could be true. All of those are possibilities. Let me show you an example of that. And I'm not going to prove this one formally, just for the sake of time, but I'll leave it as an exercise. Prove if there is an x such that p of x and q of x, that logically implies there is an x such that p of x and there is an x such that q of x. Okay. This is a statement that you can prove. The proofs are going to look very similar to the proofs we've just done. There's going to be some rules of universal specification, some rules, sorry, not universal specification, but I guess we don't have a name for this one, but if there exists an x, you can just say p of x, rule of existential something or another. Do we name it in here? This was off script as well, but it was a good question, so I wanted to go into it. Looks like we don't name it, but I would call it something like rule of existential quantifier or something. You would prove this, but this is not true the other way around. And let me just explain why in words. I won't prove it, but it is not true that there exists an x p of x and there exists an x q of x logically implies there exists an x p of x and q of x. So what is the difference between these two statements? In the first statement, there's only one existential quantifier. That means I'm claiming there's one x that makes p of x true and q of x true at the same time. So if there's one x that makes p of x true and q of x true, that means that something makes p of x true and something makes q of x true. In fact, it's the same thing. But it doesn't work the other way around. It's not true that if something makes p of x true and something makes q of x true, then the same thing has to make them both true. So here's one example. If p of x is even and q of x is odd, it is the case that there are even numbers. It's also the case that there are odd numbers, but it is not the case that there's a number that's both even and odd. Okay. Questions there? This was a really good topic. It was not something I'd planned to spend so much time on, but I'm glad we went there. Wouldn't it be a good example to show something that works for the first but not for the second? Not sure exactly what you mean. Works for this statement? Okay. So sure. So this shows why this is true. As an example, p of x can be, let's say, x squared equals 9, and q of x can be x minus 3 times x plus 7 equals 0. So the solutions to p of x are x is equal to plus or minus 3. And the solutions to in q of x are x is equal to 3, x is equal to 7. So it is true that there exists an x such that p of x and q of x, that number is 3. That means there exists an x p of x, 3. There also exists an x q of x, 3. However, there are other answers for p of x and q of x as well. Right? You could use 7 to show there exists an x q of x. If I just wanted to prove there exists an x q of x, 7 is a perfectly fine example to come up with. If I just want to prove there exists an x p of x, minus 3 is an example I can come up with. But if I want to show there exists an x p of x and q of x, 3 is the one I have to find. Good question. Okay, let's hop back on track. You can have more than one quantifier. No reason I can't say something like p of x comma y is the statement x is greater than y. That's a perfectly fine open statement. So if a variable is within the scope, this is a technical term that just means inside the parentheses of, is within the scope of a quantifier. It is called bound. Otherwise, it is free. So if I write there exists x, p of xy, x is a bound variable, y is a free variable. Okay. And I can have more than one quantifier. So here's my question. Does the order of quantifiers matter? Got a yes in chat. Good. So let me give you an example. What is the difference between for all x exists y, p of xy, versus exists y for all x, p of xy? What do these two things mean? Giving you a minute. I want you to really think about it. It's easy in lecture to go into like auto writing down notes mode, but actually stop, challenge yourself. What do these two statements mean and what's the difference? Good. So I see some good answers in chat. They're true. They're getting at the idea. I want you to push further. I want you to translate these two statements less directly into English. So this first statement says, for every x, there exists a y such that p of xy. That literally means for every x, there is a y such that x is bigger than y. But what does that mean in a general sense? It means every number is bigger than some other number. Every number for all x is bigger than some other number. There exists a y that's smaller than the x that I picked. How can we write this mathematical statement in a nice English sentence? For one number, every number is smaller than it. Good, we're getting there. I want an even nicer English sentence. This is good, by the way. I would perfectly accept for one number, every number is smaller than it. But an even nicer English sentence would be, there is, right? There exists, so there is a smallest number. Yeah, good. There exists a number such that all other numbers are smaller. All other numbers are bigger based on the way I've written it. But you've got the right idea. There's a y that's smaller than all x's. Yeah, there's a smallest number. Okay, so which one of these statements is true and which one of these statements is false? got a lot of left one is true. The answer is I tricked you. It was a trick question. You can't know. I even wrote this one in green and this one in red. It was all the trick. It depends on the universe. If my universe is the real numbers, then this statement is true. You can always have a smaller number. Just go more and more negative. This one is false. There is no smallest number. If my universe is the positive integers, then this one is true. If I say positive, then 1 is the smallest integer. If I say non-negative, then 0 is the smallest integer. And this one is false because there's nothing smaller than 1. Interestingly, it can't be the case that both are true at the same time. That would be a difficult exercise, but definitely one you could do. Prove that this implies not this. Because if every number is bigger than some other number, it's not possible that there's some smallest number. And you could prove that in a formal column type proof, but I think it might be challenging. Okay. I want to move on from that. I'm going to skip that example for time. Let's go ahead and take our break now. That's a good place because I want to shift topics again. So let's take 2 minutes now. I've got 9:07, so we'll come back 9:09. But go get a snack or a drink, whatever you got to do. Run and use the bathroom, and we'll come back in 2 minutes. We are section A02, yes. Or at least this is section A02. If you're in a different section and you're just sitting in, welcome. You're welcome here. Are we shifting to in-person? So the answer is I don't know and would love to know. The university has said that there will be a partial move to in-person classes, but more details will be coming. So I do not know. Okay, I have 9:09. Let's regather, refocus. Good quick little break. Regain the mental focus. So our main tool so far for proving for all statements has been the rule of universal generalization. But the rule of universal generalization, it just doesn't always work. So here's a statement. Every color of the rainbow is spelled with the letter E. By the way, these are the colors of the rainbow because I want this statement to be true, so sorry, indigo. I don't have an indigo marker, therefore you're not a color of the rainbow anymore. And maybe I should specify in English. Okay. So we could turn this into a logical statement. We could say C of x is the statement x has the letter E in its spelling. And then for all x in R, C of x, where R is the colors of the rainbow. Okay. So there's my statement as a mathematical statement. How can I prove it? If I try to prove it using rule of universal generalization, I'm going to run into trouble. If I just say, let C be any color in the rainbow, I don't know what to do with that. I can't find the E in the color unless I know what the color is, but then the color is not arbitrary anymore. But how do I do it? How do I show that this is true? If I asked you, is there an E in every color in the rainbow, how would you check? Yeah, check each color. I'm just going to go color by color. Is there an E in red? Yep, there it is. Is there one in orange? Yep, there it is. Is there one in yellow? Yep, there it is. How about green? Sure. Blue? Yep. Purple? Okay. I found one in each. There's no universal rule that works. I can't say, oh, it's always the last letter, because it's not. Sometimes it's somewhere else in the word. But I can always find one. So I want to check one by one. Right? That's a proof by cases. And proof by cases works because I only have 6 colors. I would run into a problem with proof by cases if I had infinitely many colors. Works great for finite universes. But what about infinite universes? So we need another tool. We need a tool that works for infinite universes. And that tool is called induction. So, theorem. The principle of mathematical induction, which is way too long, so we'll usually just write PMI. PMI is how we're going to do a proof by cases if there's infinitely many cases. So here's what this says. Let P of n be an open statement involving n if we need two things. P of 1 is true, and for every k that is at least 1, P of k implies P of k plus 1. This implication is true. Then, for all n P of n in the universe of integers that are at least 1. So how does induction work? Induction is like a ladder. If you can get on the first step of the ladder, and from each step you can get to the next step, induction says you can go as high as you want. It goes all the way up. It proves all of the cases, even though there's infinitely many. So let me do an example. P of n is the statement 1 plus 2 plus 3 plus blah, 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 all the way up to n. That sum is equal to n times n plus 1 divided by 2. I'm claiming if I add up the first n numbers, the value I get is n times n plus 1 over 2. Okay. Here is how we're going to prove this. And the template that I use for this proof is going to follow the template that's in your theorems and definitions document. And it's the theorem that I want you to follow. It's the template that I want you to follow exactly. This is exactly how I want you to do your induction proofs. And there's two ways of looking at this. You can say, oh, JD is so strict. He makes us do it this one way. He's not flexible at all. Or you can say, oh, anytime I'm asked to do an induction proof, I know exactly what the answer is going to look like. It always looks like this. So if you look at it that way, then induction is great because it's always the same. All right. For all n greater than or equal to 1, let P of n be the statement the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. I'm going to underline in blue the stuff that's particular to this proof. But everything else that's not underlined in blue is going to be the standard template. Okay. Base case. Base case is my first bullet point here. I need to show that P of 1 is true. P of 1 is true because the sum from I equals 1 to 1 of I is equal to 1, and 1 is equal to 1 times 1 plus 1 divided by 2. This is the specific stuff. This is what I want to see every time. Okay, so I have my base case. That's my step 1. Next. Inductive step. My induction hypothesis, or inductive hypothesis, thesis, which I'm perfectly fine with you abbreviating to IH. I'm perfectly fine if base case is BC. That's okay. Let k greater than or equal to 1 and suppose P of k is true. If you wanted to substitute k into your statement here, that'd be fine. If you just want to say P of k, that's fine. But this is an important line. None of it is underlined in blue. All of it has to show up every time. Inductive step or IS. This part is just trying to show P of k implies P of k plus 1. So it all gets underlined in blue. So I'm going to start with what I want. Sum from I equals 1 to k plus 1 of I. Everything I've done so far has been easy. It's been set up for the induction. Here's where I want to really start checking things and doing work. So I've got to figure out how to make my inductive hypothesis useful. And the trick in this case is that summing up from 1 to k plus 1 is the same as summing up from 1 to k plus k plus 1. These two things are the same. It's just equality. It's just saying the same thing in different ways. But this is useful because P of k tells me what this sum is equal to. P of k says that this is equal to k times k plus 1 divided by 2 plus k plus 1. And this is by my induction hypothesis. Very important that I label that this step is by my induction hypothesis. And from here, I just want to do some algebra. I'll even add here by algebra, by algebra. Good to explain how your steps are working. And now I can factor out a k plus 1 over 2 and multiply it by k plus 2. This is by algebra. And now if I rewrite this, this is k plus 1 times k plus 1 divided by 2. Again, just by algebra. I'm not doing anything fancy here. And I have shown that if I assume my induction hypothesis, I needed to use this induction hypothesis. It was a crucial step. Then this sum was equal to this side. So, and therefore, P of k implies P of k plus 1 is true. So all of this gets underlined in blue because this is all specific to the particular problem. This conclusion step is not specific to the specific problem. That should always show up. And there's a little asterisk here. You always need to make sure you're using your induction hypothesis. And then one more step, my conclusion by the principle of mathematical induction, or just writing PMI is fine, for all n p of n. Okay. This is how induction works. We start with defining our statement clearly. We prove a base case. Then we state our induction hypothesis. In our inductive step, we use our induction hypothesis in order to prove the next step on the ladder. That's our P of k implies P of k plus 1. And lastly, we get to conclude that this is true for all n. Do you have to write bialgebra for each step? No. I liked writing the steps. A lot of students like writing the steps. Bi-induction hypothesis is crucial. The bialgebra less crucial. If you didn't write those, or if they were one of our rules, one of our laws of inference, one of our laws of logic, all of that would be a good place to write that. But if there's no justification, if you're just doing math, bialgebra or nothing is fine. Okay, let me do another example. We'll talk more about induction in a second, but just want to get some examples in. Claim a truth table with n variables requires 2 to the n rows. Okay? First step. Need to give my statement clearly. Let S of n be the statement. Proof. Let S of n be the statement. A truth table with n variables requires 2 to the n rows. Okay, it's written up here. I have rewritten it in my proof. Base case. S of 1 is true because a truth table with one variable requires 2 rows. 2, which is equal to 2 to the 1 rows. 1 for true and 1 for false. Okay. Induction hypothesis. Let k be greater than or equal to 1, and suppose S of k is true. Induction step. Okay. All I've done so far, I barely had to think. My base case was pretty easy. Now I have to stop and think, why do I think this is true? So let P be a variable in a proposition with k plus 1 variables. I want to be in the world where I'm in the k plus 1 world. And now I want to somehow use my induction hypothesis. I want to somehow use that if I only had k variables, then I would need 2 to the k rows. So if P is false, by the induction hypothesis, the other k variables require 2 to the k rows. Similarly, right? Because if I fix a value for p, it's no longer a variable. That means there are only k variables, and I know how many rows I need. On the other hand, if p is true, the other k variables still require 2 to the k rows, again by induction hypothesis. Can I explain what p is again? P is one of the variables in my proposition. So maybe my proposition is something like P and Q implies S or T, right? P is just one of the variables I'm working with. Just one of the variables. If I made P false, then that's like putting falsehood in instead of P, or putting 0 in instead of P. If I make P true, that's like putting in a tautology, putting in truth, putting in a 1. Okay, so I'm going to have 2 to the k rows where P is false, plus 2 to the k rows where P is true. Is a total of 2 to the k plus 2 to the k, which is equal to 2 times 2 to the k, which is equal to 2 to the k plus 1 rows. Therefore, P of k implies P of k plus 1. Why? Well, P of k was the thing that said if I only had k variables, I would need 2 to the k rows. And now I'm saying I used that to show if I have k plus 1 variables, I need 2 to the k plus 1 rows. So it took P of k to imply P of k plus 1 is true. And now finally my conclusion, by the principle of mathematical induction for all n S of n. There is my complete proof by induction of this claim. Explain the first part of the induction step. Yep, sure. This is the most complicated part of induction. This is where the actual proof comes in, where you have to think about why what's true is true. So what I want to prove, the thing that I'm going for, is P of k plus 1. I want to show, oh, sorry, these should be S's. Forgot I had used S. S of k implies S of k plus 1. What I'm going for is that if I have k plus 1 variables, a truth table with k plus 1 variables requires 2 to the k plus 1 rows. That's where I want to get to. But all I know is that if I only had k variables, it takes k rows. I want to use that somehow. I know S of k. I want to show S of k plus 1. I know if I have k variables, it takes 2 to the k rows. I want to show that if I have k plus 1 variables, it takes 2 to the k plus 1 rows. So how do I do that? I start with a proposition with k plus 1 variables. And I want to show that it takes 2 to the k plus 1 rows. Well, in order to do that, I have to somehow take my proposition with k plus 1 variables in it and reduce it down to a proposition that only has k variables in it. And in order to do that, I pick out any variable, I don't care which one, just one of the variables, and I decide what it's going to be. I say, if P is false, that's one of the possibilities I have. That's an option. If P is false, now there's only k variables left over. I know how to deal with k variables. S of k tells me how to deal with k variables. I need 2 to the k rows. So when p is false, when this one particular variable I've picked out is false, I need 2 to the k rows. What's the other option? The other option is p wasn't false. P was true. I'm going to need separate rows in my table to handle p being false and p being true. If p is true, I make p true, there's k variables left over. I need 2 to the k rows for that as well. So those are my two cases. I combine them together. 2 to the k rows when it's false, another 2 to the k rows when it's true. In total, that gives me 2 to the k plus 1 rows. That's where I get my 2 to the k plus 1 rows. So S of k implies S of k plus 1. Good question. Other questions? Let me do another example. Really want to hammer home how induction works. Let's do one with an equality. Claim for all n, 2 to the n is larger than n. Okay. Proof. Let q of n be the statement two to the n is bigger than n. Always start with that. Next, base case. Q of 1 is true because. Okay, well, again, this should usually be easy. 2 to the 1, which is equal to 2, is bigger than 1. Right, nice, easy explanation. Induction hypothesis. Let k be greater than or equal to 1, and assume q of k. What does assuming q of k mean? That means I'm assuming 2 to the k is bigger than k. Yes, sorry. PF stands for proof. Good question. I like the answer oof, meaning the letters I've left off are OFF, but it also looks like Isabel asked the question and Ashley was like, oof, you don't know what PF stands for? Not what happened, just funny. Okay, that's my induction hypothesis. Now induction step. Now I gotta start thinking. Okay, so I'm gonna start with one side. I'm gonna start with 2 to the k plus 1. My goal is to show that this is bigger than k plus 1. And I want to use my induction step somewhere. I'm not going to write by algebra this time. So I want 2 to the k to show up somehow. I'm going to make that 2 to the k to show up by factoring out a 2. This lets me use my induction hypothesis. I'm going to label by induction hypothesis. Okay. What I have right now is 2k. What I want to get to is k plus 1. And this is tricky. I would not fault anybody for getting stuck here for a while. How do I get from 2k being bigger than k plus 1? Well, there is a trick here. This is a really useful trick. This is equal to k plus k, and k plus k is greater than or equal to k plus 1 because k is greater than or equal to 1. Right? In my induction hypothesis, I said, let k be greater than or equal to 1. I'm using that part too. Right? Use every part of the buffalo. K greater than or equal to 1. Here's k, I'm replacing it with a 1. And so what I have, if I follow this whole string of inequalities, is therefore 2 to the k plus 1 is strictly greater than k plus 1. So q of k implies q of k plus 1. Right? That was a trick. But it works. And then I can conclude, so for all n, q of n by the principle of mathematical induction. That only works with greater than or less than. Right. I'm not sure exactly what you mean. But yeah, I mean, because what I want to prove is an inequality, I'm allowed to use inequalities here. Obviously, I can't replace k with equals 1 because it's not always equal to 1. Somebody raised a hand. You want to unmute and ask? That's fine.
Yeah, sorry.
Yeah, go for it.
I wanted to ask, so is it like the same case as before where we would break it apart? Like in this case, we looked to get k just by itself, and then we got k plus 1 again after?
Mm-hmm. Yeah.
The same case where we just break it apart and then we put it back together to look for k plus 1.
Yes. Yeah. So the trick to induction is you always want to find a way to get your q of k to be useful. So in this case, q of k talks about 2 to the k, so I wanted to force a 2 to the k to appear. And then once you've applied your induction hypothesis, you're exactly right. Now, everything's in terms of k. You have to be clever and find a way to force k plus 1 to appear again. So if we go back a couple of examples to this sum, I had a k plus 1. I wanted to force p of k to appear. So I forced it to appear. And now everything is in terms of k. I have to force my k plus 1 to appear again. That's the tricky part of the induction step, is getting what you want to appear using algebra and tricks and things like that.
Thank you.
Sure. Okay, so I have 2 minutes left. I want to say 2 important things. Let's see if I have time for both. The first is that base cases are important. Here's my example. If I make my p of x the statement x is an integer, and I claim for all x in the positive integers p of x plus 1/2, this is obviously false. But if I just look at my induction step, skip base case and look at induction step, it is true that p of x plus 1, p of x plus 1/2 does imply p of x plus 1 plus 1/2. If you assume that x plus 1/2 is an integer, 1 is an integer, adding 2 integers together gives you a new integer, then x plus 1 plus 1/2 is also an integer. So even though the base case is easy a lot of the time, it's still crucial. If you just did an induction step, you could get something where there's no problem, but the answer isn't true. Okay, I don't have time to talk about the other important thing I want to talk about. We will start with it on Tuesday. Office hours later today if you want to come and ask questions. Quiz opens tomorrow, closes Monday night, so make sure you get it done by then. I'll see everybody either in office hours or class on Tuesday. Have a nice rest of your day. I'll hang out for another couple minutes for questions, but I will stop the recording here.